afternoon, everyone. Thanks for coming. Today, Gaurvi and Alberto are presenting a work that they are doing together. The title is On-the-Fly Action Classification. Both of them are a third-year PhD student, and Gaurvi is working on computer vision and applied machine learning, and Alberto with time series classification.
Thank you, Matteo. Since the introductions are already done, I'm going to jump right in. The work that we're doing involves two parts. One is taking the data and extracting the features from it, which is what I will be presenting. And then the classification part, which is what Alberto will be presenting in the later part of the presentation. So let me first define what the problem statement is. What we have is we want a system which to which we give trimmed video data. Now we are sticking to video, which and not there is the possibility of using other information like mocap information or depth information, but we want to stick to video because it's more easily available. Trimmed information, on the other hand, isn't that easily available, but this is the first step at least. So we give it trimmed videos, and what we want from the system are final decisions or labels or targets, a final action that is defined. The application for this are many, like human-robot interaction or human-computer interaction in general, surveillance, automated caption generation, medical monitoring, and others that I've probably forgotten at this time. There are also many challenges with this involved. One is that the video stream can have a variety of lengths. This can be one because an action is longer or shorter. For example, reaching action is short. Meanwhile, taking something from one place and putting it at another is a longer action. Or taking a jug and pouring something can be a longer action. At the same time, the other reason can be that I take less time in doing it. Meanwhile, maybe Alberto decided to do it and take a few more frames, which implies the length of the input would change. We might need a decision to be taken on the go, or which could mean that we don't want the action to be completed by the time we make the decision. We might need it in between so that we can then incorporate the next step of whatever application we are doing. Sequential processing of video frames requires a lot of computation power. You don't realize it until you actually try, really. Video frames are correlated and time dependent, so the information coming from previous frame needs to be incorporated when you're processing the next frames in order to come to a correct, hopefully correct decision. So we decided to use neural networks for this thing. Neural networks are a category of machine learning algorithms that are representation learning, and they are architectures with a large number of layers, although most of you probably already know this. The advantages of deep networks are they have shown exceedingly good results and seem to be incorporating or solving a lot of problems much better than conventional systems, and even in a lot of areas, but also in action recognition, they have high accuracies for some benchmark data sets like UCF 101 and HMDB 51, which have 101 and 51 classes respectively. But at the same time, deep networks also have some big problems. For example, for one, you need a colossal amount of training data to train a large enough network. And once you have it, then you need a huge amount of computation power and memory in order to actually train those networks. So how do you get around them? I'll come to that. There are techniques, and I'll come to that in a minute. First, I want to talk about this very interesting property of networks. Let's stick to image networks for now. This very interesting property that if you look at a variety of them with not necessarily the same structures, but let's say convolutional networks, you notice that even though if they are trained on a variety of data, they seem to converge to very similar filters, at least in the beginning layers, which in most cases look somewhat like this, that are they look a lot like Gaber filters, and which are they were conventionally used in computer vision techniques for texture analysis or color blobs. And so if they all seem to converge to the same thing, so we can logically say that we could take layers from one network and use it in other applications, right? So this is exactly what transfer learning is about. And is often used and is a major help in reducing the amount of training in data and computation power that we need. So networks that are available and have been trained already are there are quite a lot available these days. They're called pre-trained networks, and some examples are for image networks are VGT16, AlexNet, Inception, version a variety 1, 2, 3, 4, and also for video analysis there is Inception 3D available from quite recently. I mentioned Inception 3D. Specifically, there are others, but I mentioned this one because it's the one that we are using. Now, the reason that we chose this one is something I will get to in a bit. What I want to show you is this is the overall structure of Inception 3D, which is the structure is the same as Inception version 1 with 18 layers. And okay, once you have a pre-trained network, how do you decide how many layers is it that you want to keep from this network? So there are two factors involved. One is how similar is the original data set on which you trained your network, on which the network was originally trained, compared to your data set. And the second is how similar is the task that it was trained for compared to your task. The more the similarity, the more number of layers you get to keep. In our case, the Inception 3D had been trained for the same task, which was action recognition. So 1 point. The second part is the data set, and it was trained on a data set that had long actions, or rather activities. That is, a collection of actions makes an activity. Oops, I'm gonna put this down for a minute. So each sample in that data set was long and had, let's say, playing football or making eggs as an activity, as an action. While in our data set, things were smaller and 1 or 2 seconds in general. So that data set was slightly different. Hence, we decided to keep about 15 layers and take these 15 layers and extract features here. Now, this was, okay, in theory, it seems logical, but at the same time, we also checked it empirically, and the result was the same. So at 15 layers, we decided to cut here and extract features. Now, coming back to why is it that we decided to use this particular pre-trained network? Well, there were other networks that were equally complex and had good results, but this network, the manner in which it was trained was the thing that gave it higher capabilities. What they did was, so let's say you take an image-based convolutional neural network, and what is in there? So each layer, a convolutional layer, has convolutional filters or kernels. Let's say a 3x3 square, and each of these kernels, when trained, acquire ability to extract certain information. So initial layers extract edges, corners, small information. Later layers extract more interesting or more complex information like table, face, etc. So they extract spatial information, simpler and more complex. So these guys took Inception version 1, a very complex model, and trained it on one of the largest image data sets available, which has 21,000 classes and 14 million images. So a very complex network trained super well on a lot of information. Now, once this was trained, it was pre-trained network. Now these kernels, what they did was, for each kernel, they inflated them. That is, this replicated the same layers. So every square became a cube. So a 3x3 kernel now became a 3x3x3 cube. But it's still able to extract only spatial information. But now it's turned into the Inception 3D model with some amount of ability to extract spatial information. Then they decided to go ahead and train it on the kinetics action recognition dataset, which is the largest dataset available for actions at the time. It was at the time, with 400 classes and more than 400 videos per class. In contrast, the previously largest dataset had about 150 classes. And now there is also an upgrade of Kinetics 600, and I think soon there will be a Kinetics 800. But we don't have pre-trained networks available for that yet. We will upgrade when they do. So once this was trained, each kernel is now able to extract both spatial and temporal information from the inputs. So hence we have a very complex network with very rich kernels or weights. Now this is the same network with different graphics and 15 layers, because 15 are the layers that we decided to extract. First, what I want to, they are color coded based on the type of layer that it is. And we give it a volume. So images and the third dimension, frames, and the third dimension is time. We give it each time a volume, and through the layers, this information is compressed so the volume becomes more dense and more rich. So we have more information compact in less space. So a simpler model or classifier is then able to interpret this information to get the action that we want, the action that it is. And after this, the final, so if initially there were 9 million pixels or parameters rather, then at the end there are 300,000 parameters at the end of 15 layers. But most important, notice that the compression is not just in space, where it went from 224 to 7, 224 cross 224 to 7 cross 7, but also in time. So the 60 frames were compressed into 8 feature frames. So yeah, which is what we have decided to call them, feature frames. And we feed this into a classifier of our choice, an SVM, a singular perceptron, a convolutional classifier, or a classifier that we will be talking about next, or so for you, your favorite classifier, and you can get a prediction. You can get a prediction, or you can get probabilities, and keep those probabilities. So we decided to not come to the final prediction, but calculate the probabilities with a single-eyed perceptron and put them into this kind of a structure. First, let me define a few things before I explain the structure. What was called a video sequence will now be called a session, and what was in a video, each feature frame will now be called an event. And so for each event, a distribution of probabilities was calculated, as in the probability of it being in class 1 or class 2, or mixing or pouring or whatever action it is, and then used in the classifier, which Alberto will be talking about now. Over to you, Alberto.
Thank you. Okay, so starting from this table, where each session is correctly labeled to its class, we can think of a new decision, of a decision approach, a decision criterion that we want to use to leverage the sequential nature of the information we have of the video stream, and so be able to decide which class it belongs to from the structure of the video frames and from the feature frames that have been assigned a special probability, a specific probability. So you know that a frame has its own probability, which is estimated by a convolution of neural network followed by the single layer perceptron. And then we have n different classes. N classes because we have to classify n different actions. So far we did the experiment with 10 classes, because I will explain later what are the problems, because there are some problems in our tests. But we have then n plus 1 possible outcomes, which is in case of correct classification, in case the classifier is able to take a decision during while receiving new frames, new feature frames, we can assign a class from 0, so one of the n classes, n possible classes. But what if we cannot take a decision at the end of the frame or at a certain frame, and we want to observe something else, so we want to wait for another feature frame? We don't take a decision, we leave it to none, and we wait for other observation, if any. And then we decide what to do. Now I need to introduce a bit of quantum computing, because we need a bit of background on quantum computing to understand how the classifier works. The classifier, well, quantum computing is studying a new computational system based on properties of quantum mechanics. And the properties that we are using now are superposition and entanglement. Superposition means that we can add together any valid states and obtain another valid state, or vice versa. And entanglement is the property that, in my mind, is most important for correlating video frames, because it states that if two or more particles are entangled, they cannot be described independently of one another, so they have a tight relationship. And this is what happens in video frames, in video streams. So, well, this is again theory. Qubit is the basic starting point of quantum computing, and it's the analog of a classical bit. Cat notation is used to understand how we work. Cat notation is this symbol, and we need to map the classical bits 0 and 1 into their quantum equivalent, which are column vectors. In this case, we only use 2 classes because it's easier to follow. Then I will generalize everything to any number of classes. But in the beginning, it's easier to follow with only 2 classes. So 0, this is column vector, and cat1 is the other column vector. So we can define a new qubit state, yes, psi, as the superposition of these 2 basis Q state, the basis state, with these 2 coefficients as multipliers, which represent the probability amplitudes of each state, its basis state. And they are called probability amplitudes because the square values they sum up to 1, as in normal probability. So the entanglement is obtained by using the tensor product, which is a simple Kronecker product, and you can combine more qubits into a single one, which is expressed by this notation. Cat 011 is the entanglement of 0, 1, and 1. And a state can be considered entangled if it cannot be decomposed in any fundamental parts because you have no information about that. So you see that this is what is called generally the cat state. It's two states in equal superposition, two entangled states in equal superposition. And it's in equal superposition because this 1 over square root of 2 squared is 0.5, which is equal probability from both states. One big problem in a real quantum system is measurement, because anytime you access a real quantum system, you change its state, you modify the state. So if you measure it, you alter the state of the system, and then the system turns into the basis, the pure state, represented by the act of measuring, when it was measured. Measurement is the only way that we have to extract useful information from the quantum system, whereas in this case we use it in a non-destructive way. The good is that if it were real, we couldn't measure it many times to obtain the various estimates of probabilities for each of the states that we are need to measure. In this case, I can measure all the probabilities I need for each of the basis states, which is how we will use the system in classification. So we can measure the probability of each cat state k, pk, and if we only have two states, it's easy to measure only one and obtain the other by 1 minus the probability of states. In generalizing in a multinomial environment, so it's easy because it's intrinsically done or built in a way that it's easily extended to many classes. So you can define, as we did for two states, two basis states, we can define these n different states in which the column vector contains n values, where only one is 1 and all the other are 0. It's an orthonormal basis. So the qubit state can be then expressed as a superposition of all the basis states. All the basis states applying proper coefficients. Okay? Then we see what are the coefficients. But still, the coefficients represent the probability of these states. And I'm still linking to the table that she presented in the slide. So the probability, we calculate the probabilities because we need them to obtain the superposition of the states. So the classifier, what is the idea? The idea is that at each time step, we have, for any feature frame xt, we have a class conditional probability, which is estimated by the convolutional neural network. And being that all observations are time dependent in the same sessions, all the events are time dependent, so we can think about using the quantum classifier, well, the idea of quantum computing, to correlate these actions, these probabilities. And we define alpha I as the square root of the estimated probability. So the step is then that at each new frame in a sequence of length s, so you have different frames, feature frames in this case, not frames, but these are feature frames, you can build an s-qubit entangled state, psi I, which is created for each of the basis states by analyzing all the probabilities that have been assigned in the session. So at each new frame, you generate a new probability and you add them to the list. So for each of the basis states, so let's say 0, we can generate an entangled state which takes into account all the probabilities that have been estimated so far by the classifier, the convolutional classifier. So the state that represents the whole stream, and so which analyzes all the possible classes, is then built by combining the superposition of all the n entangled states. So each entangled state, psi 0, psi 1, and psi n-1, minus 1, is representing the combined, the the entanglement of the probabilities of each class. And then by measuring the system, we can obtain the probability, the estimated probability of the quantum system, so the state that is represented by this quantum system. In this case, what we obtain is that we measure each of the probabilities, one for all the classes that we have, and if the decision, so if this measured probability is higher than a certain threshold, and in the same time, for all the other remaining probabilities, the sum is lower than another threshold, we can reasonably take a decision that the result is that the system is representing class I. Let's say 0, 1, or I-1, whatever it is. Otherwise, we leave it to none and wait for another sample to come in. So if it is not possible to take a decision, it's left undecided, and it stays undecided till the end of the session. If it is possible to decide to make a decision before the end of the session, before the end of the video stream, it is better, and so we can take a reliable decision. Otherwise, we can consider it an error.
Okay. Just one question. Whether it's better that you don't need two coefficients, C upper and C lower, because if there are probabilities, shouldn't be one.
Yes, this was my first thought at the very beginning, but it was not, well, the problem is that I want to be confident that the remaining probabilities are not so high, and so the thresholds are not symmetrical, are not complementary. So they do not sum up. C upper and C lower are not adding up to 1, but sometimes are more than 1. Because in order to decide, if I keep it strictly to the probabilities, you end up with a lot of threshold, a lot of sessions undecided. So you relax a bit the constraint on the remaining probabilities, this part, in order to be able to decide, even if it is not strictly probabilistic. Okay. These are our classification results. I hand it over to you because you know better.
So, to present the results, first let me define the data set. So, we are using the cooking actions data set, which was acquired by Alessia Vignolo a couple of years ago. But we have decided to use only 10 of the 20 classes. This is because of the memory explosion that occurs with the classifier. And so we test
the quantum classifier. Well, I forgot to mention that one of the big problems that we have is using by using tensors, we have problems with memory explosions. So we had to limit the number of classes in order to allow for the completion of the test. Otherwise, and we also implemented a get-around mechanism, which is a kind of a sliding window that limits the number of samples taken into account at each time, and so a kind of a view in the past, because of this problem. Otherwise, you cannot cope with such a memory explosion and the system crashes. This is at the moment. There are, I have already talked about some ways to get around this problem, but they are still work in progress. Sorry.
So the number of events considered at a time are limited, and also the number of classes that are considered are at the time limited to 10 for now, but we will fix the problem in the future, since this is at a very preliminary stage of our work. So we show results which wherein the training was done on 10 classes in all cases. And we have results for single-head perceptron, a convolutional classifier, and the QEMC. Now, with these two, there is the possibility of giving it one sample at a time, but also to give them the input in batches. And in the latter case, the results are much better. Because what we are talking about here is a system which can be used on the fly, and hence has only one sample at a time, and which is why we chose to show you the results for that particular case. The training is done on, coming back to the data set has, in this case, 10 actions, 10 cooking actions, wherein there are 3 synchronized cameras recording the same action synchronously from 3 different viewpoints. The first viewpoint is a lateral viewpoint, the second one is egocentric, and the third is the exact opposite of front camera. The egocentric is a camera that is about near the head. And in all cases, the training was done only on the first viewpoint, which is the lateral one, and then tests were conducted on unseen data from the same viewpoint, as well as unseen data from other 2 viewpoints, which had not been incorporated in the first case. What we see is, as expected, the highest result is for view 0, which is because it looks very similar to the training data. And in this case, which is the egocentric viewpoint, you can imagine when you see somebody else doing an action, it is very different from if you do the same action. The viewpoint is very different, and hence the accuracy reduces in all cases quite a lot. The third case is still the same kind of view as the first, which is an allocentric view, front and lateral, but it's somewhat more similar, and hence the results are higher. But in all cases, the QEMC is able to improve on from the input that it is given. But this is the thresholds. There are a lot of things that we can try with the thresholds, and the results can be changed.
Results change a lot according to the threshold that I selected for the quantum approach, because this is what we were saying before. It depends on how you select the threshold. You get much better or much worse results, even worse than 29, depending on the threshold. So it's important to tune reasonably the thresholds, maybe doing a kind of a Pareto analysis, Pareto frontier analysis, trying to minimize or maximize the accuracy, but minimizing the other parameters in order to obtain the optimal thresholds for your task.
So there are a lot of variables involved, and a lot of decisions that we've made in this entire path so far already, and at the end, it all depends on the application that you want to work on, the application that you have, the approach that you want to do depends on what you want to apply it for. The single net perceptron and the convolutional classifier need an entire video for them to classify it, while the QEMC can classify them in the middle, and again it depends on the application that you want to use it for. The timing for each of these steps is quite high at this point, and not really applicable for real-time applications. But once we have a pipeline that is functional and good, we can then go back to each of these steps and optimize them for an application.
Yes, a quantum classifier has the advantage that, which is not negligible at the moment, which can classify very quickly. The experiment we did in all the viewpoints, the longest decision sequence is 6 steps, 6 feature frames, which represent more or less 1.5 seconds, more or less, which is interesting because it says that we can classify very quickly the actions even without waiting for them to complete, which is the aim of on-the-fly classification. And as I said before, well, we need the proper tuning of the thresholds, because these are the key to obtaining good results and real speed in classification. So we need to do other tests, we need to do more tests, either with training and with classification, also because it takes a lot of time to get full test hours to complete at the moment. So it's a long test. We could do only a few experiments, a few tests with some pairs of thresholds in order to be able to present something meaningful here. I think it's concluded.
One thing that I want to point out is also that it was never the case that the classifier never came to a conclusion. In 6 feature frames, it always came to a conclusion, which is also of interest because in this application, it is really usable.
Okay.
Questions?
So you said that you choose few pairs of thresholds and then you just apply it. So the thresholds are not learned.
No, at the moment I am not able to learn the thresholds. There are ways to learn the threshold in other approaches. One that I've been using for bot detection, which is a sequential probability ratio test. There's a way to learn the thresholds. In this case, I haven't thought about that. Just empirically proven. We do the test, we scan a lot of pairs of thresholds, and we analyze them with the Pareto frontier. So we can decide which is the best option according to what is the task that we want to perform. So if we want to be, well, one of the possibilities is that, okay, we want to have no undecided session. So you tune the properties and you analyze Pareto with Pareto to obtain 0 unclassified. Or you may want to reduce, have the highest speed in classification. So there's another pair of threshold that it's suitable for having higher speed of classification. It depends on what your task, what your aim is.
So now they are depending on the data you have now.
Yes, absolutely. But according to the experience, when you train on a sufficiently wide data set, you obtain thresholds that are more or less reliable. According to my experience of bot detection, I think that if you have a big data set in which you can train very, very stable, you obtain thresholds that are reliable for the task that you want to perform. Other question?
In terms of this upper and lower bound that don't depend on I. So
It depends on?
on I, on the class.
No, they don't. It's another possibility to specialize the threshold for the particular class, but I don't think it's easy to do that, at least at the moment, how the things are made.
Because the other point was also, depending on how you choose the threshold, you may end up that 2 classes are meeting the threshold. So
You may end up with 2 classes.
2 classes satisfying that both conditions.
Yes, it is possible, but it is the wrong choice of shadow to threshold probably. Well, what happens is that in the first experiment I did, I stopped the decision at the first first class that was meeting the constraint. So if you have a swipe on the classes, you measure it from 0 to n-1, and the third class is meeting those constraints, so you say, okay, this is the decision. Then I realized it was not really the case, because you need to complete the sweep on all the classes, and because maybe there are more than one class that match the constraint, and then you pick the one with the highest probability, highest measure probability, which is improving the results in this case. Not too much, but big. No, it is not maximum probabilities, because It's not obtained by, well, it is more or less a maximum probability of the classes, but it's obtained by using entanglement, which is not combining probabilities as a simple multiplication of the probabilities and obtaining a joint probability. It is not joint probability.
In any case, you wouldn't, you want also the null case. So the null case
Yes,
means that
I also wanted the
there are
undecided.
no high enough classes with high enough probability.
Exactly. And also I already tried to experiment also a variation on this, because instead of using the square root in the coefficient, I use, floating point values, other floating point values, ranging from 0 to 0.1 to, let's say, 2.5, 2.6, and so on. And this gives sometimes another improvement. It's a kind of inserting a degree of fuzziness to the decision. And so by using different coefficients, different floating point numbers, you obtain even better results. This, again, is specifically tailored to the single task. It depends heavily on the task. But it's another variable that we can use to tune the result.